Hi, my name is Alusan Barry. Welcome to this lesson on the applications of differentiation. In this lesson, we are going to solve our first example on the application of the idea of rates of change. Okay, remember we said rates of change can be connected using the chain rule, right? So this question says a spherical bubble, so a bubble, imagine you know bubble, soap bubbles, okay? A spherical bubble is decreasing in volume at a rate of 2 centimeter cubed per second. Okay, so here we have a balloon, but imagine this was the cube and it is decreasing. Imagine there is a hole in the balloon and it's decreasing in volume. The volume is decreasing at a rate of 2 centimeter cubed per second. Okay, so we 2 centimeter cubed per second, and we are asked to find the rate at which the surface area is diminishing. Okay, is diminishing and is diminishing when the radius is 3 centimeters. When the radius is 3 centimeters. Something you have to note, like I said earlier, this the volume, the decrease in volume will be represented with a negative sign. Remember, it is decreasing. Okay, so we have to say minus 2. If it was increasing, it would have been positive 2 centimeter cubed per second. Okay. I was just explaining here. Let's go down, give ourselves some space so we can solve this problem properly. Okay, just rewriting. The problem says a spherical bubble is decreasing in volume, at a rate of 2 centimeter cubed per second. Okay, we are asked to find the rate at which the surface area is diminishing. That's also decreasing. Okay, diminishing. So this you have to know your vocabulary. Okay, diminishing when the radius is 3 centimeter. Okay, so this is our problem. Let's try to find a solution. Okay, now like I noted, I remember, say note, I'll just abbreviate rate of change to be ROC, rate of change, okay, of the volume will be negative. Okay, it will be negative because they told us the bubble's volume is decreasing, right? So therefore, since, in fact, you should know since the volume is decreasing. Okay, now so this implies the derivative dv dt is minus 2. Okay, because we are told the volume is decreasing with respect to time. Okay, remember the centimeter cubed per second, so it is decreasing with respect to time. So the dv, rate of change of volume with respect to time, dt, is equal to minus 2. Okay, so let's give ourselves some space. Now, what we have here, you have to note, like I said, the formula, you have to know that, okay? Because the two key things we are looking for will be the volume of a sphere. Let's just put sphere here, and then the volume will be equal to, the volume of a sphere is 4/3 pi r cubed. Okay, and the question also noted the surface area. Okay, the surface area of a cube is equal to 4 sorry, of a sphere, 4 pi r squared. Okay, once you need these two formulae, you need to know them. Okay, so now let's go on because the question actually asks us to find the rate at which the surface area is changing. So let's just say s, the s, the dt. Okay, the s dt is what we are looking for, right? Well, now using the chain rule, you will notice that the s dt can be found by saying by the chain rule through the s. If we know the rate at which the surface area is changing with respect to the radius, okay, and the rate at which the radius is changing with respect to time. Like you just imagine a visual cue like the r's, the dr's cancelling each other. We are still going to be left with the s dt as we have here, right? But now we have to first of all also imagine that we need to find. We already know the SDR because we have the surface area here, the formula, Okay, so but the R dt is a problem, right? So but we can find the R dt, the rate at which we say but the r dt, the rate at which the radius is changing with respect to time, can be equal to the rate at which the radius is changing with respect to the volume and the rate at which the volume is changing with respect to time. So you can imagine this as well crossing out each other and you are still being left with the r dt. Okay, this can confuses many people when you see the r dt here, because what the question gives us, because we know the formula for the volume, we already have dv dr. So but if you find the reciprocal of this, you are going to get dr dv. Okay, this is what we are doing, because if we say dv dr right now will be equal to we say we are going to differentiate the expression. We multiply by 3 and then we subtract 1. Okay, so this is going to be 3 multiplied by 4 over 3 pi r. The 3 minus 1 will be 2, so that's squared. So 3 can cancel 3, so we have dv dr as 4 pi r squared. Okay, so this is dv dr. So we have this, but we can, if we find the reciprocal of dv dr, this is going to be 1 over dv dr. Okay, so this is like saying 1 divided by dv dr. If we want to change this to multiplication, we can say 1 times dr over dv. So therefore we have dr dv. Just so if you are wondering how we get dr dv. Okay, so once we get this, but now this just means we are going to say 1 over 4 pi r squared. Okay, uh, let's don't be confused. Let's get some more space, and then we can see how we go about this. Right, now we know the rate of change. So the rate of change of the surface area, okay, this is what we are looking for. Let's just say here d s d t, sorry, dr, the s dr, the rate at which the surface area is changing with respect to the radius here will be, we are going to multiply by 2 and then we subtract 1 from the power. So this will be 8 pi r. Okay, so now let's go on and find our derivative here. So now if we can find the r dt, we know now the r dv will be 1 over 4 pi 1/4 pi r squared, okay, multiplied by dv dt. What did we get as dv dt? The rate at which it's changing with respect. dv dt was -2, remember, okay, -2. This was given to us in the question. So here we can cancel out 2 cancels with 4, so we are left with, so here it comes 2 times into itself 1 times, so we have 1 minus 1 over 2 pi